Hello. In the last lecture, we had introduced the discrete Fourier transform and an algorithm called fast Fourier transform to compute DFT. And after that, we had introduced the notion of a convolution of two vectors. Given two vectors of n components each, the convolution denoted by A star B was defined in the following fashion. The ith component of A star B was given as the sum of products of the components of A and B such that their indices add up to I. So, this was the original definition of the convolution, and we had shown that this expression can be broken down into these two parts. In the two cases when I, the index I, is between 0 and n minus 1, then this is simply Aj B I minus j, where j goes from 0 to I, and when I is greater than n, then the difference between these two is that the j ranges from I minus n plus 1 to n minus 1. In this same sum is now split into these two. We had then an observation which showed that these two sums can be then combined into this single sum of this kind, j going from 0 to I, but the difference is that we have to redefine vectors of 2n length each. A prime was original vector A followed by n zeros, B prime similarly was original vector followed by n zeros. So, both of them are now 2n length vectors, and then their sums, the product sum of the products of the terms A prime j and B prime I minus j, j going from 0 to I, gives you exactly this term. Now, one thing to remember here is that the convolution is actually a vector of length 2n minus 1 precisely. The reason is that there are only 2n minus 1 possible ways we can have these values when both of them are 0. So, I can be 0 when both indices are 0, and the largest they can have is n minus 1 plus n minus 1. So, 2n minus 2, but we actually extend it to 2n minus 1 by really assigning the value 0 only. So, we will think of this as a vector of length 2n, and here we have extended these two base vectors to 2n length, and then we have defined the following expression for the convolution. And the last thing we did was stated this theorem, which is a way to compute the convolution using discrete Fourier transforms and inverse discrete Fourier transform. So, let us just go through this. This is again saying that we have A and B which are further extended to this 2n length by padding n zeros here, n zeros here. Then we take the Fourier transforms of both of them. So, these are again vectors of length 2n each. This symbol indicates that you are multiplying the 0th component with 0th component. That would be the 0th component of this product. First component with the first component will be the first component of this product, and so on. So, this is component wise multiplication, and this is again a vector of length 2n, and then you compute the inverse Fourier transform, and the claim is that that is precisely the convolution of the two original vectors. So, let us go through the proof. Just the definition of these we have already shown is this product, my mistake. So, we have to now talk about the discrete Fourier transform of the two. So let us just take the ith component of this product, which is f2n a prime f2n b prime. The ith component of this, as we mentioned, this is nothing but point to point multiplication. So this is nothing but f2n a prime I into 2n b prime I. Now recall that the discrete Fourier transform of a prime was assuming that w denotes the, or rather we will use another symbol s. Let us suppose s is the 2nth primitive root of unity. So we will have s power I j times a prime j, and j is going from 0 to 2n minus 1. This times another sum s I k, k going from 0 to 2n minus 1 b prime k. I am going to write down, suppose s is the 2nth root of unity. So that is what s denotes. We can then combine these two to get j going from 0 to 2n minus 1 and k also ranging from 0 to 2n minus 1, s I j plus k a prime j b prime k. So let me define a new variable which denotes j plus k as L. So that would be some L, j plus k will go from 0 to 4n minus 2, but again I am going to extend it to 4n minus 1 and setting down the last element as 0. So that I am going to split into two sums. First, from 0 to 2n minus 1 j, from 0 to L s power I L, this is I and this is L, a prime j b prime L minus j, plus the remaining range of L, which is 2n minus 2n to, okay, for now let us write down 4n minus 2, because that is the largest possible value of our variable L. S I L a prime j b prime L minus j. Okay, so let us look at the second term. The sum of the two indices is L, and that is at least 2n. Hence, at least one of these indices has to be n or more. And what we notice is that the value of our vector beyond n minus 1 is 0, both of these vectors. So this product will always vanish. So this will be 0, and we can only focus on this side. So, we have now L going from 0 to 2L minus 1 sum j 0 to L S I L A prime j B prime L minus j. Let me take this term out of this sum, and you have L 0 to 2n minus 1 S power I L sum 0 to L A prime j B prime L minus j. All right. Now, let us focus on this expression. Instead of I, if I plug in L here, then this expression is same as this expression. So, what we are seeing here is the Lth component of the convolution of A and B. So, this reduces to L from 0 to 2n minus 1 S I L okay, and that is nothing but the Fourier transform of this vector. Notice that this is a 2n length vector and S is 2nth root of primitive, the 2nth root of unity. Hence, this is precisely the ith component of Fourier transform of A star B So, we have f 2n A prime to n B prime equal to f 2n A star B. The reason is that ith component of this is equal to ith component of this. Hence, these two vectors are equal. So, we can say if we take inverse transform on both sides, we are going to get A star B. The right hand side will be A star B and this side will be f 2n inverse of f 2n A prime f 2n B prime. So, that is what the claim was, and this lets me compute the convolution by computing two transforms and one inverse transform. Recall that the complexity of computing Fourier transform was n log n. In this case, it is 2n log of 2n, which is same as order n log n. So, the total cost of for the time complexity of this, the time complexity is computation of 3 Fourier transforms. Remember, inverse transform is also a transform. By just taking the suitable root here, we will get the Fourier inverse transform. So, the 3 operations of each of complexity n log n, and over here we have these 2n multiplications, but 2n multiplications take time 2n, because we are assuming that all basic arithmetic operations take unit time throughout. So, the total cost is nothing but 2n log of 2n times 3, or even this is same as order n log of n. This is a very efficient way to compute the convolution, because if you try to do in a brute force manner, then you are going to perform one multiplication for each of these components. So, there are somewhere around 0 to 2n different multiplications. So, almost n square multiplications, not almost but precisely n square multiplications. So, the brute force algorithm would take order n square time. Now, let us take an application of convolution. Let us suppose we have two polynomials, p of x, which is sum ai x power I going from 0 to n minus 1, and qx is sum bj x power j going from 0 to n minus 1. Then the product p times q, the coefficient of x k, just to align myself with the old coefficients, let me use another index. So, let us say the index of the the coefficient of x power I in the product would be Of course, I will go from 0 to 2n minus 2, but again I will let it go to 1. Over here we are going to have the sum of all the products whose indices add up to I. So, I will write down sum a k bj, where k plus j is I. This is exactly the result of multiplying these two polynomials, but this is exactly the convolution. So, what we have here is x I a star b I. So, what you notice is that to compute the product of the two polynomials is essentially computing the convolution vector. Hence, the product of two polynomials which are given explicitly, that is to say polynomials are given as coefficients of each of the monomials, then the product can be computed in order n log n time. So, this is indeed an efficient algorithm to compute the product of two polynomials, and as we just had seen, a brute force method will take order n square time. Now, I am going to describe another form of convolution which will be handy in some other application, and that is, in fact, we will describe two such convolutions. The first one is going to be called positively wrapped convolution of, again we have these n component vectors. Now, in this case, what we do is, let me just visually describe this. So we have this A0, A1, An minus 1, B0, B1 to Bn minus 1. Suppose this is I, then the ith component in normal convolution, we multiply these two, and we multiply these two and these two and these two, and we add them up. But in a positively wrapped convolution, we continue. This is index I plus 1. So this should be multiplied with A minus 1. That is index minus 1, which when wrapped is this. So this will be multiplied with this, and this will go with this will go with this, and this will go with this. So we will have actually several terms here. Together, the ith component of, now I have a complicated notation. This indicates positively wrapped convolution of A and B. The ith component is, I am going to write down this expression in these two terms separately. We will have Aj, B, I minus j. Well, first of all, just keep in mind that this, unlike the regular convolution, is only an n component vector. There are only n components, so I only ranges from 0 to n minus 1. J will go from 0 to I, 0, 1, 2, 3 up to I, and then the second term we have j going from I plus 1 to n minus 1, I plus 1 through n minus 1, Aj B. Now the index for B is negative. Now, all we have done is we added n to it, so it is n plus I minus j. So this accounts for these terms. Similarly, now we can define negatively wrapped convolution. I just want to make sure, n plus I minus j. So negatively wrapped convolution is exactly the same thing, but this contribution is with a minus sign. So that we will express as A star minus B I is j going from 0 to I Aj B I minus j minus j going from L I plus 1 I plus 1 to n minus 1. Okay. So the range is same. This is the same term that I am going to write. This is the same term as this, only difference is we have a minus sign. A j B n plus I minus j. Now our objective is to compute these using Fourier transforms. So that is what we will do next. And what I am going to do is effectively use the algorithm for this to compute this. So key thing is to compute this, and then using that we will get this one. So now let me just state the claim. we have theorem which says that A is A0 through an minus 1 and B is B0 through Bn minus 1. Okay. Then A star plus of B is F inverse F of A everything looks very similar, but this time we are dealing with the original vectors themselves, not the extended vectors. We are just taking the regular Fourier transform of A, that of B, then we do point to point multiplication and then take the inverse Fourier transform, and this we are claiming is nothing but the positively wrapped convolution of the two vectors. So, let us see how is that. Once again we are going to follow through the same steps. I am going to take the ith component of this F n A F n B I is F n A I into F n B I. That now I am going to use W to denote the nth primitive root of 1. So, that would be j from 0 to n minus 1 W I j A j times similar term k 0 to n minus 1 W I k B k. Again we will play the same trick. I will combine these two, j from 0 to n minus 1 k 0 to n minus 1 A j B k, and again I am going to define a variable for j plus k. So, let us say L denotes that variable. Now, that variable will have range from 0 to 2n minus 1. Again the last term we add. So, let us write down L, and I think I am going to write them into two parts. 0 to n minus 1 first is this is j from 0 to L, W I L W I L A j B L minus j, A j B L minus j, and then we have a second term. Let us write down that plus. So, let us say now L goes of course from n to 2n minus 1. This time suppose L, let us say L is n plus alpha, alpha is 0 onwards. If this is the range, then j at the highest j will be n minus 1 at the uppermost limit, because we have actually vectors of only n components. So, j can at most be n minus 1. At the lowest, it will be lowest when k becomes, or the second index, this becomes n minus 1. So, that would be n plus alpha minus n minus 1, which is alpha plus 1. So, now I know the range of my j, which is alpha plus 1 to n minus 1. What is alpha? Alpha is n minus l. So, I will take n minus l plus 1 to n minus 1, and w I l a j b l minus j. So, this is what we get by substituting new variable l for j plus k. Let me verify l minus. Okay, I did make one mistake. Our alpha is l minus n, not n minus l. So, I will have to put l minus n here, l minus n plus 1. Okay. So, the right hand side I can continue. I can again put this in here to get sum L from 0 to n minus 1 W I L sum j going from 0 to L A j B L minus j plus. Now, look at this expression. Let me substitute for L another variable L prime, which stands for L minus n. N is a constant. So, I am going to write everything in terms of L prime, assuming that L prime is L minus n. So, this is L prime, which goes from 0, because L is n to 2n minus 1. So, this will go from 0 to n minus 1 j L prime plus 1 to n minus 1. Right. W time power I times L prime plus n. Now, let us just quickly look at this. W power I L is W power I L prime plus n, which is W power I L prime into W power I n. Notice that W power n is 1. So, W power I n is also 1. So, this goes away, this is gone, and this is just I L prime. I am going to write down W I L prime A j and B L prime plus n minus j. Now, since L prime is a dummy variable, I can replace that by L again. So, this is L 0 to n minus 1. If I replace L prime by L again, notice that L is different from the old L. This is just L prime rewritten as L. So, we are going to get the same term here. This range is same as this. So, I can combine the two and I can write down this as I L. And now, I am going to put these two terms as j 0 to L A j B L minus j plus sum j going to L plus 1 to n minus 1 Aj Bl plus n minus j. Okay. Now we have an expression for positively wrapped convolution. Notice that this expression is same as the expression we have got there. This is same as this. So we are going to get some W I L, L going from 0 to n minus 1, A positively wrapped convolution of A and B L, and that makes it F n of A star plus B ith component. So we combine the two and get F n A F n B is F n of A star plus of B. Once again, all you do is take F n inverse of both sides and you get your desired expression. So now finally we are going to state how to compute the negatively wrapped convolution. As I had mentioned earlier, we are going to use this particular method, but we will have to have a trick here to be able to introduce a minus sign for the second term of the convolution. So what we are going to do is the following. Let me just state the claim in the form of this theorem. So let A be this A0 through A n minus 1 and B is also n component vector, and S be the primitive to nth root of 1. Now define two vectors A prime as A0 S A1 S square A2 S n minus 1 A n minus 1, and B prime similarly B0 S B1 S square B2 S power n minus 1 B n minus 1. So instead of dealing with the original vectors, we have inserted powers of S, increasing powers of S with each component, and now we are claiming that let C prime be the F inverse of F of A prime This is the same computation, only the vectors have changed. And let us say this is what we are going to get, where C prime is let us say C0 C1s C2s square Cn minus 1 Sn minus 1. So write this vector in this form, then our claim is that C, which is nothing but C0 C1 through Cn minus 1, is nothing but the negatively wrapped convolution of A and B. So, all we have to do is modify the original vectors into these two vectors, do the same computation that we would do for positively wrapped convolution, and then if I divide the respective component by power of s, I am going to get the negatively wrapped convolution of the two original vectors A and B. Now, let us take the what exactly C prime is. C prime is nothing but the positively wrapped convolution of A prime and B prime. That is what we have proven earlier. So, let us just look at what we are getting. C prime is A prime positively wrapped convolution of A prime and B prime. So, let us write down the expression for that, which is sum. We had expressed it in two parts. Our I goes all right. So, I need to write down the ith component. C prime I is sum j going from 0 to I, A prime j, B prime I minus j plus j going from, so let us just copy that. The range for the second part is I plus 1 to n A prime j B prime n plus I minus j. Okay. So, we have this. The prime components are nothing but the corresponding s values here we can plug in. We are going to get okay. So, we have s power j and I minus j. So, this is s power I, A, j, B, I minus j, j going from 0 to I plus sum. Now, this time j, so we have s, this time this is contributing s power j and this is contributing s power n plus I minus j. So, we have n plus I here, A, j, B, n plus I minus j. And you notice that you have s power n, which is minus 1. So, I can now write down this as sum S I A j B I minus j minus sum S I, okay, j goes from 0 to I here and j goes from I plus 1 to n minus 1 here, n minus 1 here also, A j B n plus I minus j. So, we have these. So, now we can take S I common and we are getting this as S I sum j going from 0 to I A j B I minus j minus sum. Again j was from I plus 1. So, j from I plus 1 to n minus 1 aj b n plus I minus. Now, look back at the definition of negatively wrapped convolution. This was precisely the ith component of the negatively wrapped convolution of A and B. So, we are getting C I prime as S I and A star minus B I. Now, we have defined our C components as C prime component divided by power of S. So, Ci is Ci prime by S power I, hence this is nothing but A star minus B I. So, what we have found is that the vector C is precisely A star minus B. Now, how much time does it take to compute this? To compute all the powers of S takes order n time. In each step I can compute the next power. So, I got these. I can then in order n time multiply them to individual components. So, this work is order n. Otherwise, we have just 3 Fourier transforms to compute. Over here we have to divide by S. Now, just a remark there that division by S, notice that S power 2n is 1, hence division by S is like multiplying by S power minus 1, which is S minus 1 is nothing but S power 2n minus 1. So, if I have S power 2n minus 1, then I have to just multiply successive powers of that term to each of these to get rid of these. So, that takes order n time again. So, the entire process takes order n plus order n log n. So, the time complexity again is again order n log n. So, we can compute all the 3 convolutions in the same time complexity. I have given you the application of the regular convolution in computing the product of 2 polynomials. We will see an application of these convolutions in the next lecture. But before we will talk about the next lecture, I would like to make some remark about the ring in which Fourier transforms can be computed. Recall that we said the Fourier transform or discrete Fourier transform can be computed in a ring R which satisfies 2 conditions besides being a ring, commutative ring with 1. What we wanted was that 1 over n must belong to our ring, and 2, there should be a primitive nth root of unity, primitive nth root of unity. But if you notice in our computations we also needed primitive 2nth root of unity sometimes. So, where exactly we have such a ring? So, one of the rings obviously is nothing but the field of complex numbers. In complex numbers we have e to the power 2 pi I over n. In terms of the picture, this is the real axis, this is the imaginary axis, and this angle is 2 pi by n. So, this is the nth root of unity, and it is a primitive nth root of unity, because when you multiply with itself, it will make twice the angle and so on. The nth root, nth power of that will take you to this, and before that it will be something else. It will never come back to unit before that. So, this will be the W you can use, because complex numbers form a field, 1 over n is always there. So, both these conditions are satisfied, and we can compute the Fourier transforms, discrete Fourier transforms in this domain. But sometimes we are interested in, notice that working with complex numbers means there is always a problem of precision. You lose certain precision. These computations are not going to be exact. So, we are sometimes interested in working with integers. Hence, what we will do next time is describe another ring where we can work with integers without loss of any precision. Provided we take large enough a ring, we will have a range of rings, infinite rings, and then we will actually discuss the Fourier transform in that ring.